For the function f of x equals negative 3 plus 5x cubed, find the derivative of the inverse function f inverse of x at the point x equals negative 8. All right, so the first knee-jerk reaction here is for students to see this x equals negative 8 and want to plug that into the function f. And to be honest, you can. You can take negative 8 and you can plug it into your function. It's going to result in a fairly large number, as you can see. Because 8 cubed, if you do that on your calculator, let's see, 8 cubed is 512, and then we multiply that by 5. All right, and it's negative, but so is the 3, so I'll just say plus 3, and so it's going to be negative 2563, which is a pretty large number, okay? Now, here's the thing. This is not how we're going about the problem. So, the key here is the point x equals negative 8 is on the inverse function. It's not the one we're interested in on the original function. All right, so the original function has points like x and f of x, or xy, which is the same as x f of x. The inverse swaps those things. So we have yx is a point on the inverse function. So it's more like f inverse of x and x. Okay? Now, so that's going to change how we use the negative 8. Let's take a look at this function and see how this is all making sense. So here's that function. So this is negative 3 plus 5x cubed. Now, if you notice, it's a standard cubic function, and I've got the point P here, which I can move around, and you might be able to see, okay, the coordinates of the point. What I'm looking for is a point on the inverse of this function. So let me pull the inverse. All right, so well, there we go. There's the inverse. So what I'm looking for is x equals negative 8 on the inverse function. So if I drag, well, I can't drag q actually. I can drag p and q just follows along. So I want to drag q to where x is negative 8 there. And I'll just get it as close as I can because it can't be perfect. I don't think so. So here I am where x is negative 8 and y is negative 1. So here's the thing. What I am really looking for here is where I have negative 8 on the inverse function. So to do that, I can actually solve the original function as if x equals negative 8 is a y value there. So, for instance, if I take negative 8 and set that equal to negative 3 plus 5x cubed, let's see what happens. All right, so first off, I add 3 to both sides. Canceling that out, this would be negative 5 equals 5x cubed. Dividing both sides by 5, I get x cubed equals negative 1. And if I take the cube root of each side of this equation, dealing with cubes, I don't have to worry about a plus or minus. Negative cube roots are okay. So I get x equals negative 1. So this is an x on the original function. So the point in question is the point negative 1, negative 8 on the original function. Okay? So looking back at the graph, notice where point P is. X equals negative 1, y equals negative 8. This is the point in question. Okay, now the next thing that I need to do is I need to figure out what the slope of the tangent is on the derivative, or on the inverse. So looking at the tangent on the original function, if you'll notice, that relationship is always going to be that the slope on the original function is the inverse of the slope on the inverse function. So it's just the reciprocal. We just flip it. So effectively, if I figure out what the slope of the derivative is here, I can just invert it and come up with the slope of the derivative over there. An alternative would be to find the inverse function and then find the derivative of the inverse function and go that route. But this will work okay as well, and actually probably will be a bit easier. So I have f prime of x is the derivative of a constant, negative 3 is 0. The derivative of 5x cubed would be 15x squared. All right, now the derivative evaluated at negative 1 is 15 times negative 1 squared, which is just 15. So that's the slope of the function at point P, which is on the original graph. So notice I've got close to 15 there. The inverse is just 1 over that. So 1 over that is going to be 1 divided by 15. And, oh, there we go. And I can say that the inverse function's derivative evaluated at negative 8 is going to be 1 over 15. And that's my final answer there. An alternative route would have been to get the inverse function. And to get an inverse function, you take the original function, which is y equals negative 3 plus 5x cubed. You invert, you swap your x and your y. So x equals negative 3 plus 5y cubed. That's just a trick we use from algebra. We resolve for the variable y. So this would be x plus 3 equals 5y cubed, or x plus 3 divided by 5 equals y cubed. So y is the cube root of all of this. Now, the thing is, if I'm going to find a derivative, a slope of the graph at a particular point, I need to get the derivative function, so I need to differentiate this, and then when I work that out and evaluate at negative 8, I'm going to come up with 1/15 directly. But you have to admit that this function is a little bit more difficult to differentiate than this one. And, well, the original, which was up here, I suppose. And because of the ability to use the relationship that inverses have inverse slopes at their tangent lines, we can choose whichever one's easier to do and go with that one.